Thank you for the invitation. I'm sorry not to be there. I should have been there. So I have half an hour, 20 minutes. How long?
25.
20.
Sorry, say it again. We didn't hear you well.
I have 25 minutes. Can you hear me?
Yeah. 25 minutes is okay, plus 5 for questions.
Okay, I try to keep the time, but if I'm going long, just interrupt me.
Yes.
And of course, if you have a question, feel free to interrupt, and we will discuss your questions. So yes, I was saying thank you for the invitation, and sorry for not being there. What I want to talk today is brief report, updates report on the status of numerical relativity simulation and results on binary neutron star mergers that are focused or are employed for inferring equation of state constraints from observation of gravitational wave and light. So let me start from the final application, short summary of the final application, or what we are thinking, or what most of the people are thinking. So these are constraints on the equation of state after the 17 observations. And basically what we do here is the mass reduced diagram. You should see my pointer. We start from a prior of 2 million phenomenological equation of state that satisfies very generic hypotheses like GR and causality. They also satisfy the maximum mass constraint. So all the stars have more than 1.97 solar masses, and the gray contour is the 90% confidence of this prior. And what we do is, what we did was to perform a Bayesian inference of both the gravitational waves and the kilonova. And this is the edge, the blue edge area, and you see that there's, if you go at mass 1.4, there's about there's a constraint around 12 kilometer, 12.2 plus minus half kilometer. This is what the inference delivers, and we can further fold in the nicer result, and this will obtain again a consistent result with the inference that is the green edge area. And what nicer does, you see it hopefully from the plot, it basically shifts a bit the 90% confidence area a bit on the right, and you get the measurement of again 12.3 plus minus 0.7, a little bit larger uncertainty than the other two pieces. So this game has been played by various groups, and there are using different models, also using different observation. This is a summary of some of the results, and essentially all of these are consistent results so far. And this somehow suggests that these analyses are still prior dominated, not in the sense that they're not informative, but in the sense that the observation does not allow yet very precise measurement. So what I want to talk about is what goes into this analysis from numerical relativity and gravitational wave modeling perspective. So let's start first of all from the gravitational wave. And here what you see are inferences on the 17 data of the tidal parameter that has been reperformed by Rossella Gamba and other people in my group, paying special attention to minimizing the biases in waveform model. So this is a particularly relevant aspect because the tides are measured at very high frequency. This is shown in the second plot. And here waveforms are more uncertain. And of course, we are using match filtering techniques. So these are inference method that relies on the waveform model. So what we find is that for this particular event, systematics are not dominating the inference. They're not dominating yet, but they are present. And they are actually very well visible if you consider an analysis of the waveform models themselves. And also if, and also if you consider the plot of this posterior that is presented in the slide. So the moment is not possible, of course, to say what is the waveform model that should be used, what is the most accurate model. What is possible to say is that different model gives different result. And one possible way that you have to minimize these biases that we found is to cut the analysis at 1 kHz. And doing so, we lose a bit of SNR, and the statistical error gets slightly larger. By doing that, we obtain results that are actually consistent for all the possible waveforms that are reasonable waveforms that are available today. And in this way, also, as you see from this plot, the posterior for this reduced other parameter, lambda tilde, shifts a bit on the right, and actually differ a bit in shape from, let's say, previous result from LIGO-Virgo analysis. And in particular, they are not, they are one peak only. So they are not bimodal anymore. And from this posterior, what we get is this 12.5 kilometer plus minus 1 or something kilometers. That is the first contribution of the first plot that I've shown. So note that other group has suggested to cut this analysis at high frequency. In those cases, the motivation was more suggested about the data quality at high frequency. But still, there are several groups that have proposed to do that. So waveform systematic were basically okay here, but what is going to happen? Well, what is going to happen is that we are going to be dominated completely by waveform systematic when we will move towards high precision measurements. And this plot shows, this plot here on the left, it shows that, it actually shows the systematic bias in the lambda tilde parameter divided by, or relative to the statistical error, and for increasing SNR. So the different lines are essentially due to the different waveform models, and these are some of the most modern waveform models that are available at the moment. And as you can see, as soon as high precision measurement would start to become possible, then the systematic error becomes of the order or larger than the actual statistical error of the measurement. So perhaps here a naive comment would say, okay, but why don't you use numerical relativity to select or develop this type of waveform? Well, the short answer is that numerical relativity also comes with error. And at this level of precision, a fraction of a radiant over several cycles does matter. And this is shown in the table on the right. That tells that some of the best waveforms that are available now are not sufficiently accurate for measurement at SNR, where systematic error are relevant. So improving the numerical relative precision is something necessary for the future. And this is something that we have been working since a long time. And I will simply report the most recent result. One of the main issues for waveform quality is the numerical dissipation that we have in our GR plus hydrodynamic simulation. In particular, the use of low-order numerical scheme that is something that is to some extent necessary in hydrodynamics. So a possible approach that we have followed here is to combine, perhaps this is a bit technical, but if people are interested, is to combine a high order unlimited numerical flux, at least in smooth region of the flow, with standard finite difference volume flux in regions where entropy increases. Okay, this is a very simple and efficient scheme. And this picture shows this entropy and the density of the matter. And basically what happens is that here in the regions where entropy is very high, here, if you can see my cursor, and also here, there you apply your standard finite volume scheme. And this is effectively activated there. But all in the other region where the entropy is actually the dark areas, what you are effectively doing is to apply a numerical method that does not dissipate much or at all. And this works to track effectively the surface of the star, you see here, but it also works tracking the collisional shock here that happens during merger. And as an example of this, this is a test of the numerical method. This is the profile, velocity profile of rapidly rotating neutron star. And you see in the first panel that this method helps, or basically works very nicely to maintain the initial equilibrium profile. This is what we expect. Whereas other method dissipates here and you lose the control of the radio. And also the method is convergent, as you see in this bottom panel. And if you apply this method to binary neutron star calculations, what you find is that we find a significant improvement with respect to previous result. We find a convergent waveform, and we find waveform that converge sufficiently fast, such that faithful waveform, which is the measure that we have for the waveform quality, can be actually obtained with about 200 cube grid points for SNR 80. So we start approaching these regions where systematics might dominate. So this is one possible way forward in the near future that we will have. So let's move to the kilonova inference. Sorry. And for what comes to the kilonova observation can effectively constrain the reduced tidal parameter and the mass ratio. For example, if you have a bright blue component as the one that has been observed, this indicated the presence of a massive disk or sufficiently massive disk. And numerical relativity simulations show that the mass of this disk correlates relatively strongly with the reduced tidal parameter and the mass ratio. So in the case of the only observation that we have, this is immediately translated into lower bounds on this parameter, which is shown in, here in this plot. And this bound is actually happen to be complementary to the weakest bound that you can find from the gravitational wave information. So here we have performed some Bayesian analysis of kilonova data, and what we use is a numerical relativity informed semi-analytical model due to Urbino-Perego, a framework that allows us to explore different components and different geometrical effects. And we have actually focused on model selection and found that anisotropic models with actually 3 components that would represent dynamical ejecta, wind component due to neutrino, and another wind component due to the disk, are actually preferred by the data with respect to either isotropic ejecta or spherical ejecta or models with less components. Okay, and this is interesting because these results are from a pure Bayesian analysis, but they are compatible with what we observe in simulation. So we have run a number of simulations with the same chirp mass as the event, a different equation of state and mass ratio. We have calculated the ejecta and the kilonova, and here are some summary plot for the ejecta property, so mass, velocity, mass, and electron fraction. And the dots are the different components of the wind or of the dynamical ejecta. And instead, the boxes are the masses and velocity of the ejecta inferred, just assuming 2 components, kilonova generated by 2 components and spherically symmetric, so the famous blue and red components. So you see from, as you can appreciate from this plot, it is not straightforward to interpret this 2 fitting component as originated from the actual dynamical and wind ejecta, because these are not compatible with what is predicted by the simulation. So for example, the ejecta, the dynamical ejecta, usually that we simulate have a too low mass and velocity. The winds have too much mass and too low velocity. So it is not immediately possible to interpret this two fitting model as the ejecta that we actually observe in simulation. And so, of course, this suggests that we need improved model, both on the simulation side and on the Bayesian analysis side. And one important aspect in the simulation is the model of weak interaction. And these plots collect, again, the dynamical ejecta and dynamical mass and the dynamical ejecta velocity for almost all the simulations that are available in the literature. And the different colors highlight the different neutrino scheme that I use in those simulations. When they are gray, it means these are a polytropic model and there's no microphysics. And well, as you see here, already restricting to the dynamical ejecta, the prediction can be very different based on the neutrino scheme. In particular, leakage scheme that are here in green systematically have lower masses. The scheme that includes neutrino absorption effect, and also polytropic equation state is the simplest thing that you can do as a large spread and reach the largest masses and the largest velocity. In any case, all these parameters, all these different data sets can be fit with relatively simple function of the reduced Adler parameter and the mass ratio. We capture broadly the main feature of this ejecta. So a bit more in detail, here is a comparison with between a simulation with leakage, so neutrino pooling only on the right, and a same simulation that also include a scheme for neutrino absorption, column 0. And what you see here is that the mass has distributed as a function of the polar angle, and you see that the two different treatment of the neutrino actually imply a different mass distribution in a geometrical sense. So the electron fraction is higher at all the latitude. And the electron fraction is actually higher at all the latitude, which you see in the bottom part. So these ejecta properties are quite important to then determine the kilonova light, and it seems that there's a parallel between what we find in the Bayesian analysis and the difficulties or the challenges of the simulations. And so this motivates the needs of exploring more advanced scheme for simulating weak interaction and neutrino in particular. And we have recently implemented the green scheme. This is based on the truncated momentum formalism, so this is called M1. And differently from any leakage scheme based, this scheme is supposed to perform a bit better for fixed sources. Actually, it simulates optically thick regime, and so it's supposed to be better, at least on long time scales. And it can also account for non-equilibrium, out of equilibrium effect. And comparing with our previous scheme, we find quantitative differences. And in particular, what we see is that there is a neutrino radiation that is more intense along the rotational axis. This is expected because there's less baryon there. Interestingly, here in general, with respect to the leakage scheme, we find larger electron fraction in all the direction, both on the equatorial and the polar axis. And interesting, on the equatorial region here, these are ejecta more on the equatorial region. This material is shielded from the neutrino from the remnant, but is still irradiated by the emission from the disk. So there is still a difference between the electron fraction between the polar and the equatorial component, which again reinforces the idea that the kilonova has to be or will be anisotropic, and there will be a viewing angle dependence. Also, in this simulation, we found that there's a inner remnant that is actually modified by the presence of trapped neutrino gas. We find systematically lower luminosity with respect neutrino luminosity with respect to leakage, And perhaps interesting, since there is a lot of discussion about this, we also do not find any, we also find no significant out of equilibrium effect in the remnant oscillation that have been predicted by scaling argument by some author in the literature. Okay, briefly, this is just a technical note. There are essentially only two M1 grid schemes that are used at the moment in merger simulations. And our implementation followed closely the implementation of Foucault. But differs in two important aspects. One is a flux scheme that actually captures properly the diffusion limit with the central scheme. So this avoids to have to deal with the ill-pose type of heat equations. And the other important aspect is that we do not approximate the collisional sources, and we include all the terms, all the full velocity dependence in the sources. And this is actually important, as you can see in this plot, even in very simple, even in very simple tests in the diffusion limits. So the different curves are different approximation of the sources. Only the non-approximated, which is the blue one, actually matches the reference solution that exists in this case. Okay, a few words about future development before I want to introduce the last topic. So looking at the next step, one important issue that I think almost all the group working in this field recognizes that we need to study long-term evolution of the remnant, in particular the disk and the disk wind, which are not very well quantified. And for example, we know that the remnant, the neutron star remnant, are typically produced with an excess of angular momentum with respect to equilibrium neutron star. This is what this diagram here on the right shows. And because the gravitational wave timescale becomes rapidly very, very long, the evolution of this remnant is actually governed by the interplay between cooling and viscous processes. And interestingly, in these dynamics, if remnant expands sufficiently far out, nuclear recombination can generate winds, and this means and actually eject a lot of matter, like 40% or more. And this means that the remnants that we would classify as hypermassive neutron star based on the equilibrium property for the same baryon mass would actually become stable after losing all this wind mass. So this is not very well understood, and of course it requires long-term simulation, require this type of sophisticated neutrino scheme I talk about, requires to resolve an HD effect, and also to start from a realistic conditions that, so the neutron stars are in an orbiting phase and go through mergers and so on. And towards this goal, what we are doing at the moment here in Vienna and elsewhere is to develop highly scalable codes that can take advantage of exascale HPC resources. And these are some preliminary, yeah?
You're still like 5 minutes.
Yeah, I am on time.
Okay.
And these are preliminary results that shows actually full production binary black hole simulation on 10 to the 4 and to the 5 CPUs with a very high parallel efficiency. And this improves over more than a factor 10 actually over current numerical relativity production code. So we hope, I mean, we do have similar result also for matter, and we hope that this would be a way to meet the challenge with this type of multiphysics evolution. So in the very last 2 minutes, what I want to mention is another part of the future. So as a last topic, how about post-merger emission? So what you see in this plot is complete gravitational wave spectrum of binary neutron star, which includes, beside the spiral and merger, which includes also the emission from the remnant here. So we have developed models to describe this entire spectrum. These models are consistent and unified. And these are based mostly on attaching fitting one-body model with simple analytical model that are in any case informed by numerical relativity, in particular using equation of state insensitive relation for the property, the main property of the spectrum. And if I can change slide. One of this relation connects the main peak frequency of the spectrum with the maximum density in the theory diagram, and which is shown here. And so in principle, it is allowed to measure the maximum neutron star density by a measurement of the post-merger. And this is, the other plot shows an example of constraint on the mass reduced diagram that combines the inference with the spiral merger only, that's the red part, and instead the complete model, which is in blue. And this is then the minimal SNR detection threshold, the minimal SNR that allows the detection for post-merger. But this means also that the spiral merger signal is very high SNR. So that actually the detection of the spiral merger signal only is very informative at all the density, because it's a very high SNR. And can capture, as you see, and can almost capture even an equation state which is out of the 90% confidence of the trial. However, the high densities are biased in this particular example. And this shows that if you include also the post-merger, you can actually properly infer the maximum mass and the maximum density. So on this, if I still have half a minute on this, again on these lines is possible probing of equational state softening. So the post-merger model that we use actually builds on a tight relation between this peak frequency and tidal parameter, which is shown here on the right. And one may wonder whether a post-merger signal can help detecting equational state effect due to hyperons or quarks. And the idea is that these effects appear sufficiently high density, and the spiral signal will not be affected by the presence of these particles. But the remnant then might be more compact, oscillate time frequency, eventually collapse much earlier. So we have an artificial example, of course, of this, and in this case we are considering an equational state with hyperons. And you simulated this, again, full Bayesian analysis, and what we find is that it is in principle possible to find signature of this effect as deviation from the equational state in independent relation. So now this does not mean that if you have such a deviation, you will have detected quarks and hyperons. So there are caveats in doing this. First of all, the obvious one, you are simply violating an empirical phenomenological relation that simply might not hold in that regime. And the other caveat is that this typically happens in a very small window of binary parameter, at least if you choose sufficiently precise equation state independent characterization of the frequency. That is also not necessarily in one of the parameter, but it could happen actually. You could see this effect actually depending on the binary that you are considering. You could see it more as an effect on a frequency shift, or more as an effect on the time collapse. It's actually a morphological change that you are looking for. So there's not only one quantity to look at. And very importantly for the analysis, what we have introduced in this paper, which is, I think it's a nice important thing, are recalibration parameter. So recalibration parameter allows you, this technical thing, don't want to go in detail, but it's a technical thing that allows you to include in the inference the actual theoretical uncertainty of the particular empirical and equational state independent relation that you use. So only using those, you can actually estimate whether the violation is 1 to n sigma significant with respect to to your input. So there's some caveat. Okay, I think I'm out of time. These are my conclusions that I will simply let you to read. I think I shared also the PDF, so you should be able to find. Briefly mentioned that all our waveform and also dynamical ejectment profiles and almost everything relevant from the runs are publicly available on our website. And finally, if PhD and postdocs are interested in work on gravitational wave and numerical relativity and general computational astrophysics, there are PhD positions and postdoc in Thank you for the attention, Sonia.